I hope you can hear me, and I'm even more hopeful that I'm broadcasting twice, once using this my iPad, and I'm hoping very much that you can see the screen that I'm sharing with my iPad. Is that correct? Can you see it?
Yeah. Yes.
Wonderful. Okay, good. So this talk will be about superconductivity. And the topics that I want to start the discussion with is an issue in the context of superconductivity that you don't find in most of the generic textbooks on the topic. And I thought this might be useful just to get a somewhat different perspective of the issue. So I want to talk first, and for a significant part of this first lecture today, about the concept of off-diagonal long-range order. Why do I want to do this? Sometimes we have to make certain approximations when we describe a many-body system, a strongly correlated material. And we do perturbation expansions, we sum up certain diagrams, sometimes we use renormalization group techniques, large N techniques, and so forth to do so. But it's always good to have something that is rigorous, that is exact and non-negotiable to hold on to. And this is the concept that I want to discuss today in the more than half of this first lecture, namely the concept of off-diagonal long-range order. So I will precisely define what I mean by that. And then we will move on and discuss an issue of the pairing instability and perform a fermionic renormalization group today within a weak coupling description. Tomorrow we will do more non-quasi-particle strong coupling theories and so forth. Good. But of course, we need to remind ourselves a little bit what we are talking about. This is my 30-second summary of superconductivity experimental facts. Clearly, there is the historically first and probably also most famous observation that the resistivity of a superconductor changes as you lower the temperature, the transition temperature, the resistivity vanishes, and we have a zero resistance state. But to some extent, much more fundamental is, of course, the Meissner effect, where we have a superconductor. This is a circle here in orange, is in a magnetic field where I'm drawing in green the flux lines. And once we go below Tc, the flux is expelled from the system. And there's a version of this problem when this is not just a sphere, but maybe a more complicated geometry, such like a torus, where once the superconductor here inside the torus has expelled the flux, we can keep still in this non-sigly connected material, we can still trap flux in this hole. And if we calculate the total flux integrated over this area, here, then we find that the flux is a multiple of a quantized object of the so-called flux quantum given here, which is given in by the ratio of the Planck's quantum and the electrical charge. And then there's a mysterious factor 2 here that, of course, we all know has something to do with Cooper pairs. And we want to understand in a much deeper, beyond weak coupling instability, why there is this 2 inevitably in fermion systems. So this flux quantization and the Meissner effect turns out to be something, and this was understood very early by Fritz London, is something that can be understood in terms of macroscopic quantum coherence. So if you look at the orbit of the electron in the hydrogen atom, you also find that in the end of the day, the flux inside the orbit is quantized, something that follows from the single valuedness of the wave function. So to some extent, we can look at the superconductor as a giant quantum state or giant molecule, whatever you want to call it. And a sensible question in this context is how would we characterize a state of macroscopic quantum coherence? And this question was answered. And it was answered in a very interesting way and historically first, in fact, for bosons in the context of boson condensation. This goes back to Penrose and Onsager in the 1950s, and it was then generalized to the context of superconductors by C and Yang in the early 1960s. So this is something that we want to discuss and draw some conclusion of, and these conclusions, some of them actually were only published this year. So it is still a rather ongoing discussion. So what do we mean by, and the concept that both of these, or all these three papers focused on were so-called density matrices. And depending on whether we are looking at bosons or fermions, you need to look at the so-called single or two particle density matrix. So let me define exactly what I mean. So if we have a density matrix rho, and it's a single particle density matrix, it may depend on all kinds of quantum numbers, such as spin, and on the coordinates of the particles, r and r prime. And what it is very simple. It is the expectation value of the creation operator of a boson or fermion at position r with spin alpha and the corresponding annihilation operator at a different position and for a different spin. It's a very straightforward object, if you wish so. And this is the single particle density matrix. We can also look at the two particle density matrix, which is rather analogously defined alpha, beta, alpha prime, and beta prime of R1, R2, R1 prime, and R2 prime. And there's a bit of a nuisance of writing all of this, but once we can go through the details. R1 and R2. And now psi beta prime at R2 prime, and psi, the dagger here, psi alpha prime at R1 prime. So once again, in this case, we annihilate here and create at a different position. Here we take two electrons at R1 and R2 prime. We annihilate them in the corresponding spin and then look at the correlation with the creation of two of those states further away at distances R1 and R2, and with accordingly different spins. So these objects have very general properties, and we consider them as matrices. That will be our logic. For example, in this case, the matrix indices of the single particle density matrix, the matrix indices are R and alpha, and R prime and alpha prime. So we combine all creation and all annihilation coordinates and quantum numbers in one meta index. This becomes a little bit more elaborate when we look at, say, the two particle matrix, because then we combine all of those R1, R2, alpha, and beta into one big index. So therefore, this continues to be just a matrix of two indices. They are a compound index of all these many, many objects. And for example, we can easily calculate, say, the trace of, say, the single particle matrix alpha. I don't need to write on the indices like this. And this would, of course, be the sum over alpha and the integral over the d-dimensional space of psi alpha dagger of R psi alpha of R. And clearly we recognize now that this is nothing else but the particle density in the quantum number alpha. If we sum over alpha, this will be the total number of particles. Right? Total number of particles. So we have a matrix and it has a trace that sums up to the total number of particles. We can do a similar exercise for the two-particle density, and there's nothing particularly profound about it, but these traces of these matrices are well understood and can be easily written down. So now any matrix, and these matrices turn out to be Hermitian, therefore they will have real eigenvalues. So they're Hermitian. So they have real eigenvalues. So therefore, we can find also there, and they have the same right and left eigenfunctions, and everything is very much the same than what we know from quantum mechanics. So therefore, we can expand in eigenfunctions. And so let me write this down. I have the density matrix, and let's look at a very specific example to make it. We want to look at the example of spinless bosons. I'm still quite a bit away from superconductivity, but as you see, the notation for the single particle is a bit easier than for two particles. So all the conceptual steps we can do in this a little bit simpler example first, and then we have a good idea how to proceed from there. So I'm just expanding this matrix. Now there's no spin index. It's again a little bit easier to write. And I'm summing this over all the eigenfunctions. I give them an index p. The eigenvalues I call n of p. And the eigenfunction phi star are phi p of r prime. This is the generic expansion of an Hermitian operator in terms of its eigenfunctions. And so in the operator language that we know from quantum mechanics, this looks a bit like this, right? Where we have rho and if we just take the corresponding matrix elements, then we're going to get what we see here. Very good. So now we know that the sum of these NP here is nothing but the trace. So we know that the sum P NP is N. The sum of the eigenvalues is the trace. And there are a number of different ways by which you can obey this relationship. One is, of course, say you have of order n eigenvalues that are each individually of order 1. And then you sum them up and you get something of order n. But there's another way of looking at this. And this is, of course, fundamentally important in the context of Bose-Einstein condensation, where you have, say, one eigenvalue that is by itself already of order n, and then maybe many, many, many other eigenvalues that are individually of order 1. And then you can still obtain something that is of order n. And we are very familiar with this. And we want to repeat the logic of Bose-Einstein condensation briefly in this language of density matrices. You will see how powerful the concept is in just about, I would say, 10 to 15 minutes. So let's consider Bose-Einstein condensation of non-interacting bosons. Of free bosons. We are doing this in order to get a feeling for how to work with these density matrices. So if we have translation invariance, then we know everything about the problem, because the eigenfunctions are just the normal single particle eigenfunction, which is that this is 1 over the square root of v times some plane wave. And the eigenvalues are at any finite temperatures known to us, namely they are given by the Bose distribution function. So we know everything. And we can now analyze this problem from the perspective of diagonal long-range order. Which I haven't even properly defined, but let's empirically make our way forward. So there are, as we all know very well, there are two different regimes. That are separated by the transition temperature of Bose-Einstein condensation, which is ultimately of the order of h bar squared over m times the density in 3 dimensions, right? And there's some factor. I have it here, the zeta function of 3/2, 2 pi, and so forth. That's not important. So this here is the volume, will be the density. So one regime is, of course, when the temperature is above T Bose-Einstein condensation. We know what happens in this case, namely, all the NP here are of order 1. Each state is occupied by its thermal weight, but there's nothing special about any specific state. So what happens in this case, we can do without much hard calculation. We see when the momentum here, the chemical potential will always be negative. If you increase the momentum, for example, for usual dispersion relation of p squared over 2m, and the momentum increases and the energy increases, increasingly the occupation will be smaller. It will be, in fact, exponentially small. So as I increase the momentum here will decrease exponentially, and the characteristic scale on which this happens is given by decay. So NP looks like this. This function of p, and it will just decrease in some way exponentially, and the scale will be 2 pi over the de Broglie wavelength of this problem, which is nothing else but in its order of magnitude h bar or the square root of m k Boltzmann and t. So this is, I mean, undergraduate statistical mechanics, occupation decay exponentially, and of course now I can Fourier transform this, which is exactly our density matrix, as it depends on the difference of 2 points. It will be 1 over v, times the sum over all the eigenvalues, e to the I p r minus r prime. This is just this sum here. But of course, we know if I can write this in the thermodynamic limit. Say 3-dimensional integral. NP, sorry. So the Bose function has to be transformed here, right? Sorry. So I can write this, and essentially what we will get is something that decays like e to the minus r prime over the thermal de Broglie wavelengths. So there will be different powers up front of all of this, but this is an exponentially decaying function. I Fourier transform it, I still get an exponentially decaying function. It's not a whole lot I can do about this. So what I find is that at large distances, this object here decays. And this is a property, even though I know all of these wave functions, all of these eigenfunctions, I still find at large distances not much knowledge of, say, correlations of taking a particle out here and adding it there. On the other hand, of course, we know very well what happens below the Bose-Einstein condensation temperature. Below the condensation temperature, we have one state that is macroscopically occupied. So for T smaller the Bose-Einstein condensation temperature, there's one state, let me call it N0, which is of the order of N. And of course, now we see we have what I mentioned earlier, that one eigenvalue of our density matrix is extensive. And now I can, of course, write down my density matrix one more time. Sum over P, NP, E, the I, P, and then there's 1 and divided by the volume. Now there's now exactly one eigenvalue that's of order n, and this gives me, if I take this explicitly, alpha times n over v, and then all the other ones. Now all of those here will at large distances again decay, because they're also decaying at large momenta. So this will for r, sorry, for r minus r prime to infinity, it will go to 0. However, this term clearly survives. And we see that even if I take the limit for r goes to r minus r prime goes to infinity, this is at p equals 0. There's no spatial dependence anymore. That's a completely homogeneous system. And even if my Bose condensation were to occur at a finite momentum, it would just give me a phase factor. So what I find is that in the limiting case of r, r prime, r minus r prime to infinity, there will be something that will be n naught times the eigenvalue of this state and the eigenfunction at r prime. Now, this is a result that we obtained for the free electron gas, for the free Bose system, sorry, in the limit where we are in the Bose condensed state. It was straightforward. It is essentially just a reformulation of what we know for Bose condensation. But what Penrose and Onsager realized early on was that this definition actually doesn't rely on having non-interacting electrons or having in any way a system that is weakly interacting. And therefore, they defined the effect of off-diagonal long-range order exactly in this fashion, that on the one hand, we have this large distance limit being non-trivial, and in addition, n naught be of order n. So one eigenvalue is of order n. Later on, we will also discuss what actually happens when we have multiple eigenvalues that can be of order n. But for the time being, we stay simple-minded and want to look what happens with such a scenario. So from now on, this will be our definition of a state with off-diagonal long-range order. We ignore that it's that we got motivated from the ideal Bose gas, and all of this, what's been written down here in this orange box, can equally be applied to any other problem. And we can ask, what are the consequences of this behavior? And most interesting consequences occur when we look at the properties of such a Bose system in a magnetic field. So what we are now doing is we are pretending that we have a charged Bose system. The bosons carry a charge E, and we want to find out what happens with this charged Bose system in a magnetic field. And of course, you know what I'm doing here is I'm preparing us for the Meissner effect and for superconductivity of fermionic systems. And I'm doing this in the case of bosons simply to distill the essence. And we will do the entire calculation.
Yes. There's a question from the audience.
Oh, please go ahead. Yes.
Hello?
Yeah, please ask your question.
Okay, yeah. Hi, Professor. I have a quick question. So in this formalism, how to see that thermodynamic limit is important in order to have the phase transition, or it is actually not really important?
Yes. So I haven't really talked about a phase transition, but it's a good question nevertheless. I think we have to have a thermodynamic limit in order to make sensible the discussion that we have a distance that are infinitely far, and that we can sensibly define that one eigenvalue is qualitatively different from the others. So I don't think you can, yeah, it's a very good question. I don't think you can have this definition without the thermodynamic limit, because really all what we are doing here is about a limiting procedure. So yes, I keep track of what terms of order n, but just like in thermodynamics, n is assumed to be is assumed to be large. Otherwise, we wouldn't have the transition. Yeah. So without thermodynamic limit, none of this would make any sense, I would think, because we cannot sharply distinguish between these two states. Yeah. If you weren't satisfied with the answer, so just yell at me, and you don't need to just ask questions. I can stop, right? At any moment.
Please continue.
Great. Okay. So what we want to do now is, so very good question. We need to be in the thermodynamic limit. We want to look now at charged bosons. And of course, charged bosons we can look and analyze and investigate in a magnetic field. So the Hamiltonian we want to discuss first is an interacting problem. I'm writing it down here in first quantization. We can easily write it down in second quantization. So we have here some momentum operator of the J's particle minus E over C times the vector potential over 2m. And we have some potential. So at the moment, I therefore consider arbitrarily strongly interacting problems, and we will make rigorous statements regardless of the strength of this interaction. But what I'm not doing is at the moment that I will introduce a lattice. We will introduce the lattice as we move on. Again, we do things in small steps here and increase the level of complexity. For the time being, this is our Hamiltonian. This is a problem that we cannot solve in general, right? It's an interacting many-body system. We cannot solve it, but we want to make rigorous statement about its properties nevertheless. And that's the beauty of the approach. So for the vector potential, we want to look at this problem first in the limit of a homogeneous magnetic field. We consider a homogeneous magnetic field. B. And the most natural way to write down the vector potential, and we want to stay gauge invariant in the entire formulation, is to write it as follows. I'm introducing a specific gauge. This probably has a name, but I keep forgetting it. You know this better than I do. I take I think it's the Coulomb gauge. It doesn't really matter. But of course, I keep this function here arbitrary, and therefore I can, in principle, represent with this function a generic gauge. This is my vector potential, and now I want to do something that is, I think, a really cool trick. What we will is we have a system in a homogeneous magnetic field that is by itself translation invariant. It's translation invariant because there's no external potential that breaks translation invariance. The homogeneous field, the field is constant in space. So therefore, it seems completely natural that if I take my system, or if I take my system and translate it, that I should get the exact same symmetry, the exact same system, sorry, right? Because the system is completely translation invariant in that constant magnetic field. However, my vector potential will clearly change if I change my coordinates and do a perform a translation, because it depends explicitly on R. Now, as we will see right away, this must imply, intuitively already clear, that such a translation ought to be representable as a gauge transformation. So therefore, what we will do is we will perform a translation where we go from position vectors R to R plus or minus, how do I do it, minus A. A, B, some arbitrary translation vector. And now we can look, how would clearly the potential doesn't change, right? If Ri and Rj are both being shifted, the difference is unchanged. The momentum operator doesn't change because it's a derivative with respect to R, which doesn't depend on this shift. However, what does change is the vector potential. So we can easily write down that the vector potential at R, now after this change, this translation, goes to the vector potential of R minus A, of course. That's the translation. But of course, we have an explicit form here. So we can write this, of course, as R being shifted by R plus A. So we get this term here and the term by R equals A. So, and I want to write this in a form that reminds us a gauge transformation, where the function chi A of R, that depends on by what amount I performed the translation, is essentially given by A scalar A naught plus phi of R. I write it down first and then we check it. Minus phi of R. So clearly, if I insert this expression here, then I'm getting the scalar product of A. So I'm shifting R to R plus A. I get a term 1/2 B cross A. Then I'm getting this phi of R here cancels my phi of R here, and I'm getting my phi of R plus A, which I have upon shifting the variables, and hence I can write down, just do this easier. There's an easier way to write this, but I write it easier like this. This is 1/2 B cross A plus phi of R plus A minus phi of R. Right? That's easier probably to recognize. I think this is. So I have the result of the shift at this position, and I'm undoing what I'm doing in going from R plus A to A for this gauge factor here. Important is...
Sorry, for the first time, you might want to dot with R.
Excuse me?
For the first time, you might want to dot with R, the position vectors, because chi is a scalar. The first time you wrote down in the last line is a vector.
Oh, yes. Hang on.
You want to dot with R.
If I want to... Of course, now I'm getting it, yes.
Yes.
And that's exactly the same as what I have done here. And now I'm getting it, sorry. You guys are rescuing me here. Good. I must dot with R. And that's exactly what I have here. Yeah? Thank you. So the important is that you see that you can write the translation as a gauge factor. We can explicitly write down this gauge factor here. There are certain, this function that remains undetermined, but it's not important for consecutive discussion. We will keep track of it consistently, but we will see it will, in the end of the day, cancel out. The important term is, of course, clearly this term here. So what I can now do is, and we are mostly happy that indeed the translation is a gauge transformation. So with this insight, I can recognize, of course, if I now have recognized that the translation is a gauge transformation, I know also how my fermion operators under such a translation must transform. So fermionic operators, we are still with bosons, bosonic operators they transform just like any boson operator has to if we perform a gauge transformation, namely e to the I times e over h bar c chi a of r times psi of r minus a. So the beauty is, as I can write down this translation as a gauge transformation, I know immediately how the translation acts onto the fermions, namely it gives it a phase, and the phase is precisely the one that we must also add to the vector potential. This way our Hamiltonian stays gauge invariant or translation invariant, whatever we want to call it, right? We know that translations are a proper symmetry. But from this alone, we now know how our two-particle density matrix transforms. So ρ1 transforms accordingly under translation. So we know that if I write down this density matrix, I can write it as e to the minus I e over h bar c times chi a of r minus chi a r prime times the density matrix of the translated system. Good. Now this, if you analyze this problem, doesn't really help you particularly. But now comes the fundamentally important step. We have a property of the density matrix under translation, or if you wish so, under gauge transformation in a homogeneous magnetic field. Now we recall that at large distances, our density matrix has this form if we have off-diagonal long-range order. If we have a state where 1 degree of freedom is in one way or another macroscopically occupied, regardless of interactions. So if we now assume this property, we can, of course, use our transformation properties of the density matrix and to express it in terms of this product. So what we find is if there's off-diagonal long-range order, we can write that phi naught of r star phi naught of r prime equals e to the minus I e over h bar c chi a of r minus chi a of r prime phi naught of r minus a phi naught of r prime minus a. And now we're in business because these properties hold for r and r prime very far apart from each other, but otherwise completely arbitrary. So it really only makes sense if this property can be translated to the two wave functions individually. So therefore it follows, and this really only follows if we have off-diagonal long-range order, that we can write phi with some phase factor times e to the minus I plus I, right? E over h bar c phi naught of r minus a. So the condensate wave function transforms in this very, very fundamental way. There's exponent missing, chi a of r, right? So let me clean this up. So now we're in a few steps ready to prove the Meissner effect. So how do I want to do this? I want to do two consecutive translations. What I want to do is I want to look at a translation from our point R to a point R minus A. And then we want to go to a point R minus A minus B. Alternatively, I want to do a translation R minus B and then to R minus A minus B. And clearly, we want to accomplish that it doesn't matter how I get from here to here. If I can relate this wave function in two steps to this wave function at this location, it doesn't matter whether I go this way or that way. And from this, we will obtain a condition. And this condition, as we will see, will give us the Meissner effect. And what I love about this derivation is that we almost didn't do anything so far, right? All we said was, let there be this property, played a little bit with gauge transformations, obtained how under the condition of off-diagonal long-range order the wave function transforms. And then we will see what happens. So let's do this. So we have this step here. Now I can do this two-step analysis. So what I do is I can write down now, this is the first step here from R to A. We have it already there. So I can equally write this, that there's some other phase factor, e to the minus I e to the plus I e over h bar c. And now I have here chi b of r minus a e to the minus I e over h bar c chi a of r times phi 0 of r minus a minus b. Clearly, I just did a two-step analysis, and of course I can do this the other way around. Chi a of r minus b plus chi b of r times phi naught of r minus a minus b. So these are two phase factors. They are the same. This function is the same, and both functions are equal to phi naught of r. So clearly, these phase factors here must give rise to the same result. So I can write the condition, therefore, is that e to the minus I e over h bar c of chi b of r plus chi a of r minus b equals e to the minus I e over h bar c chi a of r plus chi b of r minus a. So now we need to do a little bit algebra, but the steps are pretty straightforward. Let me give you the result first, and then we can try whether we managed. Chi a, write it this way, sorry, chi b of r plus chi a of r minus b can be written as chi of a plus b plus 1/2 b scalar a cross b. So how would we do this? We have an explicit expression for chi that we wrote down here. And I can now steal it oops. If I write here now chi b, I just need to write a b here. And can then also work with chi a. So then I'm getting here must be minuses, right? And this is r plus b, r minus b. And I think it is for the benefit of all of us. If I now analyze this, I can, with a few steps, demonstrate that this identity is true. So this funny combination of phase factors can be written as if I were to do the translation by a plus b, which would be this one. And this factor. But of course, if you look up here, we just switch a and b. So therefore, I can immediately rewrite this as chi a of r plus chi b of r minus a is chi a plus b minus 1/2 b a cross b. Because I need to switch a and b, but switching a and b is just giving me the cross product, a minus sign. And now we see that if we multiply one phase with the other one, we find something rather trivial that doesn't really matter. And we have a condition on this additional phase factor here, which is nothing else but saying that e to the I e over h bar and c times b scalar with a cross b equals 1. In other words, e over h bar c times b scalar a cross b is some integer multiple of 2 pi. And now we see what it implies. These a's and b's are completely arbitrary variables. I can continuously vary them, and the condition has to be still fulfilled. These are fixed numbers. The magnetic field in the system is something that has to be adjusted in order to obey this condition. N is completely arbitrary, but it's an integer. But I can even change these numbers here, these vectors, by infinitesimal amounts, and it should still be correct, because this is true for all translations. But I need to hit an integer multiple of 2 pi, and to realize this for all a and b really implies that the only solution is that b must be 0 and n must be 0. Again, because these can be continuously varied, and this is a discrete value. So therefore, we conclude from there that b is 0. So what have we accomplished here? This is the Meissner effect of a charged system of bosons. We are not talking about superconductivity made of fermions yet, but we have seen that with very, very, very general principles, all we are saying is that there's a macroscopic condensate, which implies gauge transformation on the eigenfunctions of the density matrix. We could conclude for translation invariant system that there must be a Meissner effect. This is, for my taste, the most general derivation of the Meissner effect that I know of. And it doesn't really require to do any microscopic calculation. It's an exact statement of an interacting many-body system, as long as translation invariance, of course, was obeyed. We will go back to what happens under translation invariant, under broken translation invariance in a crystal and so forth, but we will probably do this better when we look at the case of
Professor Schmalian,
yes.
you have maybe 2 or 3 minutes to summarize.
Okay, very good. I'm much slower than I expected, which is always what happens. Okay. But maybe we do at this point, we stop at this point, and you ask questions if there are any questions.
Okay, let's thanks Professor Schmalian for this interesting talk. And now we open for questions. Any questions from the audience, students and postdocs? You are given the first priority to ask questions. Especially students, PhD and master students. Anyone? Okay, so can you come up here? So there is one question.
Yes.
Hello, I have one question on the derivation. So here, I mean, you assume there is a off-diagonal order parameter, the correlation, right?
Mm-hmm.
Start from the P and P expectation value, you derive the equation for only one P. Can you show the slide? I mean the above. Yeah, I think in the below. Yeah, here. So from the 2-point function, you derive a 1-point function. So is it? I mean, but I think.
In general, this will not be possible, right? If I have a sum here over many eigenvalues, this will not be possible. But if this is only one function that stands here, since they depend on completely different variables, in fact, they are even very, very far away from each other. So this is only a function of R. So therefore, I can consider this as some trivial constant here, which I can divide through, and that will, when R prime is very, very far away, so I can always divide this by, say, phi of R, and then I'm getting exactly this quantity and with some phase factor. And then I can use the same condition for R plus A, and then I see that I get the same factor. So you can solve this, you can actually solve this problem because it sits at very, very different R. That's the only possible solution this equation can have, is that individually this property occurs. If I have this condition here for the density matrix and there's no off-diagonal long-range order, then I need to do the sum over all other states.
I see.
Right? And then I cannot draw conclusions about an individual function. I can only draw conclusions about the individual function if I have off-diagonal long-range order.
I see. But I mean, here it is expectation value. Can I think it is 2-point function or maybe just one field P1? I mean, is it expectation value or?
No, this is not an expectation value. This is really a property. This is an algebraic equation for eigenfunctions.
I see.
So we don't know really what these eigenfunctions look like for any generic system. But we do know that they obey this property. And since these R and R prime are arbitrary and far apart from each other, there's no other solution for this simple equation than this one, right? How else would you solve this equation? These functions have to be normalized by definition because we have off-diagonal long-range order. They're finite, right? And therefore, the only way to obey them is to have them individually obey this gauge property. So this basically says this eigenfunction transforms like a wave function of a quantum state, right? And this is not possible to prove if you don't have off-diagonal long-range order. The step from here to here, as you properly identified, is the most important step of the logic here. What you would do is you would just maybe I prepare this for next lecture a little bit more carefully, but I find it completely obvious that there's no other way to solve this problem because these two positions are completely far apart from one another.
I see. Okay. Yeah.
I have a question to the audience. Basically, I can do two things next lecture. I can be much faster and prepare the lecture in the usual form of slides and transparencies, or I continue like I did today and write things down. If you don't want to answer this question right now, you can tell your organizers and they will send me an email and I will prepare the talk tomorrow exactly as you like it. So either I do like I did today, and I'm very, very slow, but that's okay. At least everybody has a chance to understand. On the other hand, we will cover much more if I have pre-prepared slides, right?
Okay, so I will collect students' comments and what they want and let you know.
Thank you.
There's another question from the audience.
Hi, Professor. I think this proof is quite elegant. I think I really like it. But I have a simple question. So in principle, we know superconductivity is robust against weak disorder, right? But this argument seems to require the translation symmetry. But it seems like if I want to improve that, like to include like weak disorder, where should I do that? Is it possible to generalize this argument?
So far this argument, I found this argument somewhere in the literature, and I should provide you actually with the references. This argument was always only done for homogeneous magnetic fields. Very recently, with the bachelor students here, we could prove the vortex lattice as the first non-translation invariant case. You are absolutely right. It would be very interesting to do this for disordered system. Nobody has ever done this. It's that simple, right? So what we could prove recently was actually that you can also have a vortex lattice with quantized vortices, however, as the only allowed state. But I have not seen anybody thinking about disorder in this problem. I mean, it's a brilliant question. I don't know the answer because as you realize, right, you cannot do a translation anymore if you have disorder. But superconductivity should still survive. You need to have, I don't know how to prove it. Yeah. But it's a very good question. If you have a good idea, I mean, I can send you my notes on the vector, on the vortex lattice. Maybe you have an idea to generalize it from there.
Okay, thank you. Any other questions? So if not, thanks Professor Schmalian again. And
sorry, I have another
it's
question.
really wonderful lectures, and I think students and postdocs learned very much.